You're looking at the largest known structure in the universe, and it shouldn't. The Borealis Great Wall is so massive that it breaks one of the core assumptions of cosmology. To understand why that's a problem, you need to zoom out, far beyond Earth, beyond our galaxy, beyond even clusters of galaxies. The universe, at its largest scales, is supposed to follow the cosmological principle, which says that matter should be evenly distributed when viewed from a great enough distance. Think of it like looking at sand from far away. It should appear smooth and uniform. But the deeper we look into space, the more that idea starts to crack. At smaller scales, the universe is messy. Galaxies form clusters. Clusters connect into filaments, and these filaments create a vast cosmic web with enormous empty voids in between. This structure is expected, but there's a limit. According to our models, no structure should exceed about 1.2 billion light-years across. Anything larger would mean the universe didn't have enough time since the Big Bang to form it. And yet, the Hercules, Borealis Great Wall, is nearly 10 times that limit. So how did we even find something this big? Not by directly seeing it, but by tracking some of the most violent events in the universe, gamma-ray bursts. These are intense explosions caused by collapsing massive stars or merging neutron stars, releasing more energy in seconds than the sun will in its entire lifetime. When astronomers mapped the locations of these bursts across the sky, they noticed something strange. Many of them were clustered in one region, far more than randomness would allow. That clustering revealed the outline of an enormous structure, stretching across a significant portion of the observable universe. Now here's where it gets uncomfortable. If the cosmological principle is wrong, then many of our current models, including how the universe evolved after the Big Bang, might be incomplete. Either this structure formed through mechanisms we don't yet understand, or our assumptions about large-scale uniformity are flawed. Some scientists argue it might just be a statistical anomaly, a coincidence caused by limited data. But even that explanation has problems, because the scale of this structure pushes far beyond what random chance should produce. To grasp the scale, imagine this. Light, traveling at 300,000 kilometers per second, would take 10 billion years just to cross this structure. That's nearly the age of the universe itself. Our entire galaxy, the Milky Way, would be less than a pixel in comparison. Even galaxy clusters, the largest gravitationally bound systems we know, are tiny fragments within this wall. It's not just big, it's absurdly big. And it's not alone. Other large-scale structures like the Sloan Great Wall and the huge large quasar group also challenge our understanding, but none come close to this scale. Each discovery adds pressure to the idea that the universe becomes smooth at large distances. Instead, it might be far more lumpy and uneven than we expected. If that's true, then the early universe, the period just after the Big Bang, may have had stronger density fluctuations than current models predict. So what could explain something like this? One possibility is that dark matter, the invisible substance making up most of the universe's mass, played a more complex role in shaping structure than we currently understand. Another is that cosmic inflation, the rapid expansion right after the Big Bang, wasn't perfectly uniform. Tiny variations during that phase could have been stretched across billions of light years, eventually forming these enormous structures. There's also the uncomfortable possibility that we're misinterpreting the data entirely, and what we see isn't a single structure, but a projection effect, multiple smaller structures appearing aligned from our point of view. But here's the real reason this matters. Cosmology is built on assumptions that simplify an otherwise chaotic universe. The cosmological principle is one of those assumptions, and it allows scientists to model everything from galaxy formation to the expansion of space itself. If that assumption fails at extreme scales, then those models may need revision. Not thrown out, but refined, adjusted, or expanded. As telescopes become more powerful and surveys map more of the sky, we're likely to find even larger and stranger structures. Each new discovery will either reinforce our current understanding or force us to rethink it. The universe isn't obligated to make sense to us. It doesn't follow human expectations. And structures like the Hercules, Borealis Great Wall are reminders of that. So the real question isn't just how big this structure is. It's what it means. Because if something this massive can exist, then the universe might be far more complex and far less predictable than we ever imagined. And this might not be the largest structure out there, just the largest one we've managed to notice so far.